So, let us define this matrix Q of G as the incidence matrix. So, what is the type of incidence matrix that you have seen? Say let us now talk about directed graph. Okay, if suppose I have directed edges, okay, then how do we define the incidence matrix for this? Come on guys, incidence matrix somebody told me yesterday. Nobody has heard about incidence matrix? Yes, no? Somewhere here, give me some answer. Okay, so let me just go about this. So it is nothing but an n cross m matrix where n is the number of vertices and m is going to be number of edges, okay, and so how do we define the edges or the entries? So any ijth entry, if I look at it in this matrix, it is going to be defined as plus 1 if Vi is, I should not say incident on Ej, if Vi starts, I mean Vi is incident on Ej and how would I say, Ej starts from I, okay, Ej's tail is Vi kind of, and minus 1 if Vi is going to be the head of the directed edge, okay. Again, so I cannot use this word incident here. So Vi is the tail end of Ej and 0 otherwise. That is, if I and j, if the vertex Vi and the edge Ej have no connection between them, then we just say there is going to be 0, right. So what can we say about this matrix again? So if you look at every column, right, Ej is going to be obviously having a tail and an end, right. So every column will have a plus 1 and a minus 1 with its end points. So if you look at the column sums will be 0, okay, and the row sums would give you the in degree and corresponding out degrees also. If you add all the ones going out of I, then it will give you all the out degree. If you count the number of minus ones, then it would give you the number of in degrees, okay. So but our idea is we want to capture the column sum being 0, okay. So for this matrix, if you see, column sum is 0, and so what can we say about rank of this matrix? Can we say something about the rank? So if, okay, to talk about rank, I want to talk about number of linearly independent columns that could be there. Since we know column sum is 0, right, and so we have at least rank is 1 less, right. So we can say that rank of the matrix is at most n minus 1, right. So rank of Q is less than or equal to n minus 1, and what can we say about the other bound? So the claim is, in fact, rank of this matrix is equal to n minus 1, okay. So how do we show the other bound being greater than or equal to? So we have to do a little bit of work inside this. Say suppose, so the claim is that this is in fact equal, okay, and how do we prove this? So let me take a vector x coming from my Rn, right. So we want to talk about a vector. So take any vector and suppose this vector is in the null space. So when it is in the null space of Q, what do we mean by this? When I say x belongs to the null space, what do I mean? Qx is equal to 0, right. So but now I am making a little bit of restriction, left null space, so that what I am going to do is look at this x transpose Q, because it is a rectangular matrix. it's an n by m matrix. So, we have to be very specific about where we are. So, let us look at x transpose q. So, we know that this has to be equal to 0, right. When x belongs to the null space, that means what, this vector is being killed by the matrix, right, and it's it's in the left null space because I am going to multiply it from the left side. So, x transpose q is equal to 0 here, right. So, that means what, when why I am doing the left multiplication is for one reason. So, I take a vector x, say I multiply with a column, what is going to happen to my vector? Every column has only 2 entries, right, every edge has only 2 endpoints, vi, vj, it will be there. If that is the case, then one end will have a +1 and the other end will have a -1, right, as entries. So, this will correspond to the fact that xi minus xj will be there as an entity, which will be equal to 0 if I is adjacent to j, right, and all other places my xk, any other k position, xk is going to be 0 here, right. It will, I mean, it may not be 0, but xk into 0 will go to 0, right. So, the only term that will exist when I multiply the vector with one column is, it is going to be the corresponding positions where 1 and -1 exist, right. So, it will be xi minus xj, which will be equal to 0 now, right. So, now if we further see what does this mean, I say that xi is equal to xj here, right, xi minus xj equal to 0 means xi is equal to xj, or that also tells us that it's kind of, they are in equal proportion, right. If I have an entity for my x, then it has to be in equal proportion, right, and applying this for every vector, every column of q will tell us that this vector x should have equal components, right, every component is going to have equal value, okay. So, this tells us that in fact x is going to be a vector having equal values, some a times of 1 kind of, we can just pull out the constant. So, the vector a is going to be kind of a into 1 vector, right, some for some constant, okay. So, what does this tell us? We have already started with x to be an element from my null space, right, and I have showed you that if I have an element in my null space, this element will be of the form that every component of my vector is going to be equal, right. It is either going to be like 2, 2, 2, 2, 2 or 3, 3, 3, it is going to be of that form, right, the vector is going to be in that form. So, that tells us that any element in my null space should have this pattern, right, for different a, right. So, what does this conclude about our null space? It is generated by singleton element, right, single element, one vector is enough, all one's vector if I look at, and you can just do a scalar multiplication of that to get any other vector which is going to be in the null space, right. So, the null space of this q has dimension 1, it is a one dimensional space, okay. So, when I mean null space, I am just trying to tell you that which vectors are going to be killed, right. So, the dimension of this null space of q is going to be equal to 1. So, what does this tell us? If dimension is equal to, I mean null space has 1, then what will be rank of q? By just rank nullity theorem, you can immediately conclude that it should be n minus 1, right. So, that means what? My rank of q is greater than or equal to n minus 1, right. In fact, it is equal. Already we have also seen that rank of q is less than or equal to n minus 1, and now I am telling you just rank of q in a loose term, I am just giving you that it can be it has to be at least n minus 1. So, therefore, rank of q is equal to n minus 1. In which case are we talking about all these things? We were talking about connected graphs, right. Only then I can say equal components here. In this place, when I said every component is equal, I guarantee that like x1 is equal to x2 is equal to x3 only when my graph is connected, right. Otherwise, if there is a discontinuity, there could be two different values possible, right. Even though they are equal components, there could be two different values. So, we are ultimately talking about connected graph. So, for connected graph, this is going to be equal to, the rank is going to be equal to n minus 1, okay. So, now how do I extend this? Yeah. No, first of all, you have to translate how independence and vertex cover into my matrix language here, right. We are talking about the space, right, the space of vectors that it would generate, right. So, how is my vertex, say 2 vertices, if I say they are independent, how does that get translated into my vectors? Yeah, if G is connected. That is what I am trying to say, like here I did not say because I was looking for some blank faces. So, I am saying if G is connected, only then I can say that my vector x will have equal components everywhere, right. Say when I say equal components, I am trying to say that if x is a vector x1, x2, xn. So, obviously, when we talk about eigenvectors, what are we doing here? We are going to assign values to my vertices. Okay. So, eigenvectors give you the values actually, how these vertices are going to take part in my eigenvectors, right. As an eigenvector, how are they going to be and what will be the proportion that they will be looking into it. Okay. So, when we will do that, when we go into Laplacian eigenvalues and vectors, you will be able to clearly see what an eigenvector does on the graph. Okay. So, at present if you look at it in the matrix language, what we are trying to say is the null space, but by null space what I am trying to say is what are all the vectors that are killed by this matrix, right. So, that is going to be an one dimensional space which is just spanned by all 1 vectors. Okay. In the n dimensional space where we are sitting, or here it is n by m dimensional space, in that all ones, the Rn we are talking about, the vector x coming from Rn is going, all one vector would be killed by Q. Okay, that is the incidence matrix behavior, especially if I define it this way. Okay, for this specific definition it goes this way. If suppose I define the matrix in a different way, then there is a different set of rules that will add up to. Yeah. So, this is what we mean. So, we mean equal components, that all these are having same values. So, now the next question comes, what if there are 2 components in my graph? What can I say about my rank? So, here the main catch was by G being connected, right, and I get rank of the matrix to be equal to n minus 1, right. So, what if, so by rank being n minus 1, what I am guaranteeing here, I mean this matrix I can't talk about eigenvalues, it is a square rectangular matrix, but we will translate it to Laplacian soon. Okay. So, what can I say about if I have multiple components in my graph? So, the answer is somewhere blinking right on your face. Say if there are k components, in G, then what can I say about rank of this matrix Q of G? See here, in this place when I said we have equal values x1, x2, xn takes equal values, we had that assumption that they are going to be connected. Suppose x1 is the edge E1 is connected to E2, then what do I mean? I can tell you that this x2 value, the vector x2, so the vector x2 has to have the same value. I know since these 2 are edges, these 2 are going to be equal, right, x1 and x2 takes the same value, and x2 and x3 are adjacent means what, x2 and x3 should take same value. This is what I mean by the components having equal values, right. Suppose I have another component coming out of this graph, say I have another component sitting like this, but I know only that x4 and x5 are going to have equal values, right. When we say connectedness here, by the conclusion we can only say this, if they are adjacent then I know that the components have equal values. If they are not adjacent, we can't say anything, right. If the graph is connected, one by transitivity everything will become equal. If it is not, then what happens? We will have for the connected components I can choose a value, for the second component I can choose different values, right. So, our vector space, our null space of this 2 linearly independent vectors are possible, right. Say for x1 to x6, I can have the x1 first vector to be first 3 1 and then later 3 zeros, and x2 could be the vector first 3 being 0 and then the last 3 being equal to 1, right. So, these 2 vectors could jointly generate all possible vectors that could satisfy my criteria here, right, because I need, the only criteria is that x1 equal to x2 equal to x3 and x4 equal to x5 equal to x6. right. So, if we have two components, I have two linearly independent vectors which could generate my null space, right. Both of them will go into null space, both these type of vectors will be killed, right. So, if I have k such components, then I can generate k linearly independent vectors in similar fashion, right. So, therefore, my rank of QG with k components boils down to n minus k, right. So, now we will digress from here and we will go back to Laplacian. The idea of going back here is, I want to also give you another representation, okay. With this Q in mind, if I want to represent my Laplacian, how can I represent it? So, I will give you the answer, we will think about it. So, L of G is also equal to Q of G into Q of G transpose. Okay. So, product of two rectangular matrices. So, this is of order n by m, the second one is of order m by n. So, we will get an n by n matrix. So, how do I guarantee that this entry is going to be equal to my L of G? I look at any ijth entry of this product, how do I guarantee that this would be nothing but equal to an entry in L of G? Okay, so how do I get any ijth entry in this product? How does it look like? Take the ith row of Q and jth column of Q transpose, right. So, if you take that and if you are multiplying, when will an entry exist? If there is an edge in both direction, then what will happen? In that case, what will happen? So, in my Q, then we have to look into it. So, suppose I look at ith row, say look at Qijth entry, right. Qiej we are talking about. So, suppose we are talking about Vij a vector row wise, right. We have to, because when we talk about Qg transpose, when I take column there, what am I doing? I am taking the jth column, right. Jth column is nothing but jth vertex, right. Here it is an m by n, right. So, column is going to now represent vertices, right. So, when I look at an ith vertex and jth vertex, when will this entry be 0 or non-zero entry we will get? And of course, we have to do a summation, right. I have to take a summation of all these things. So, Qik and Qkj, right. When will this exist? I mean, if will it be always 0 or non-zero, or what kind of entry we are looking at? So, think of this, if there is an edge from I to j, what happens to my Qj? Qi, the ith row will have one, will be one side it would be 1, the other end would be minus 1, right. And apart from this, I do not think nowhere else we will have an entry coming into picture, right, in this summation, right. Everywhere else we will get 0. So, we can immediately see that we will have an entry minus 1 only if I and j are adjacent, otherwise it will become 0. If I is not equal to j and I is adjacent to j. Okay. This will also work in the other way around also, when we have j going to I also, right. What about the diagonal entries when I is equal to j? That means what? You are taking the ith row and multiplying it with the ith column, which would be ith vertex again, vertex i's column itself, right. You look at the same row, same column, you are multiplying, it is like you are taking an inner product, right. So, you will have, you will be adding all those places wherever you had a 1 appearing, right. So, it would add up to the degree of that vertex. So, therefore, we can immediately conclude that L of G is going to be nothing but Q of G into Q of G transpose. Okay. So, now from here, if I want to connect to where we are going to, like Laplacians, the other properties of Laplacians. So, we know Q of G has rank n minus k, right. So, now what can we say about rank of this product? Already we know that rank is less than or equal to n minus 1, because L has the row sum, I mean row sums become 0. So, we know that our rank is at most n minus 1. So, knowing the fact that rank of Q of G is n minus k. What can we say about rank of L of G? So, it is my G has k components, so it is n minus k, whether k is 1 or more. So, this should translate to rank of Q transpose. I mean, I just rewrote it from the definition. So, we can still see that this would be equal to rank of Q, because Q transpose is going to be a matrix which is obtained from, I mean, n cross m by m cross n matrix, right. So, we will have an n by n matrix which is going to be looking like L of G, and this rank of L of G is equal to rank of Q matrix, okay. And hence we can say that the rank of L is going to be equal to n minus k, okay. So, from here what we can immediately observe is that when I say rank is n minus k, we know that there are k 0 eigenvalues, right. That is true, right. So, connecting this to the graph, we can say that if G has k components, then my L matrix will have at least exactly k 0 eigenvalues, okay. So, the multiplicity of the 0 eigenvalues in the matrix gives us the number of components of the graph. So, this is what is our conclusion. So, number of components of G is equal to the multiplicity of 0 eigenvalue in of 0 as eigenvalue. So, this, I mean, without doing any work, just compute the eigenvalue, you will immediately know whether your graph is connected or not. If you are handling a million vertex graph and you want to know whether that graph is connected, say for example, you are trying to do something with the Facebook network or Twitter network, and you want to know whether whatever network you have, you want to know whether the people are connected in that, or there could be islands, right. Like there are some people who are connected, some people who are not connected to anybody, right. They may form a cluster. So, how do we identify all these kind of things? Just compute the Laplacian of the corresponding network, okay, converting it into matrix, and you just look at the eigenvalue of it. So, if there are more than one eigenvalue, then you can immediately say that there are clusters, that too disconnected clusters. Okay, people are there is one set of people who do not communicate outside of that community wherever they are, they do not want to connect also. So, there are certain cases where we can see this, right. So, say for example, in a religious network, if we see, there will be one sector of people who does not want to communicate outside. So, they will be within their religion, there will be a network which is formed only by them, they do not go outside, right. So, these kind of things we can capture in the network properties when we look at the spectral properties. So, this is one thing that I wanted to talk about, and there is also other properties that we want to see, we will go into this. Excuse me. And we can also see that since we have Q transpose as my Laplacian, there is also another interesting property of L of G which says that, I do not know how many have heard of this, positive semi-definite matrices. Given a matrix, we say a matrix is positive semi-definite if, I will give the general definition, if suppose there is a vector x, x transpose mx should be greater than or equal to 0, right. So, then we say that the matrix is positive semi-definite. So, here L of G also satisfies this property, okay. Why? Because if suppose I want to look at this x transpose into L into x, so what is this? X transpose into Q transpose x, right. So, if you look at this x transpose Q, what do we know from the previous, already we have seen this, right, x transpose Q, if it was null space we saw something, right. We know that at least that this will have entries looking like this, xi minus xj if I and j are adjacent, right. So, similarly if you look at this Q transpose x, there also you will have similar entries xi minus xj coming into picture. So, this product in itself translates to the summation over of xi minus xj the whole square. One xi minus xj comes from the x transpose q and the other one comes from this side for every edge in the graph. Whenever I is adjacent to j, we have this expression. So, this tells us this is a positive sum, right, sum of squares. So, the entry is going to be positive. So, therefore, we can immediately say that L of g is positive semi definite, and this property also tells you that all the eigenvalues of L of g are positive, or non-negative. Okay. So, every eigenvalue, if you look at it, they are all going to be only positive. There will be no negative eigenvalues for L of g. Okay. So, in general, we will concentrate on these kind of representation and we will study more about this. And always there is at least one 0 eigenvalue for Laplacian. We do not know about second one. So, the second one, the lambda n minus 1, if it is 0 or not, that itself pitches in lots of studies, and how far it is from 0. Okay, the lambda n minus 1, the value, how far it is from 0, that also has different perspective that you can derive from the network. Okay, similarly, your lambda 1 and lambda 2 is also there. So, all these top extreme values, maximum eigenvalue, second largest eigenvalue, and minimum is 0. So, the second minimum, when does it occur? So, all these eigenvalues have a very special role to play when you design your network. Okay. So, if you want to design a network for certain purposes, you have to keep all these things in mind and you can progress in that direction also. With this, we will continue in the next class about other special classes of matrix graphs and their Laplacians, okay, and also how this Laplacian matrix and the corresponding eigenvectors really tell you the information, what information that we get by looking at this vector. When I say I have an eigenvector, what do I get from that? Okay, so, all these things we will see in the coming classes. Okay.